Hello. Good morning. I'm really good. I'm really sorry about this, guys. Um, I turned up sick, and I just don't think I can come to school properly. So for now, let's supply the information you've missed because we really have to be on schedule. Again, I apologize about all of this. I'll just introduce you to steady flow devices for now, and then I will include cloud recordings of my class from thermodynamics for MECANG students. uh, I've solved the first two questions in there, and I will also include links to my video on YouTube solving the rest of the problems. So, ayun, right? Okay, let's just do this for now, right? All right. We have different kinds of steady flow devices available for us, right? For our analysis. And they are, basta marami to, right? Info dump session still in session, right? We have, of course, very quintessential pipes. We have nozzles and diffusers, right? We have turbines and, ang kabaliktaran ng turbines, fluid movers, like pumps, compressors, fans, blowers, electric fans are fluid movers, heat exchangers, throttling devices such as expansion valves or just valves in general, mixing chambers, and finally separators. So lots of different steady flow devices available for our analysis. So let's begin first and foremost with pipes, right? Because everything in here actually, if you guys want to think about it, are just pipes. Pipes with different things in them, pipes with different features, multiple pipes together, strung together, right? And so what are pipes? Well, I actually didn't get the definition for this on a dictionary or something. I just said that pipes are devices used to transport fluid, right? Any kind of fluid, may it be water, may it be any liquid or any gas, right? Pipes. And, right, in ideal operation, pipes are supposed to have constant pressure, right? AKA they're supposed to be isobaric. So if you are ever, what do you call this? If you are ever familiar with fluid mechanics, either maybe you guys have taken the subject or something like that, pipes are subject to what we call head loss or energy loss. Basically, because the water or the fluid inside rubs up against the walls of the pipe from the inside. What happens is that you get friction, and then they slow down. Yeah, their speed decreases, and you get head loss or energy loss. So at that point, the pressure also goes down. If your pipe is completely smooth, nothing like that is going to happen. But of course, this is ideal. Right? Ideally, it should be isobaric. Okay? And so for this section, I will reiterate things, and now I will include the first law, right? So lalagyan natin ang first law right here, right? And as you see, nothing is blacked out, or in this case, if you see some term that is colored violet, that can be zeroed, right? Usually that is zeroed. Pero don't take my word for it na usually lang yan, right? Okay? Not all of the time. We have to practice our discretion when we're doing something like this. And so now, I realized I should also give out your problem set. Anyway, yeah, this really is going to be the equation for us to get our enthalpies, our heat, our work, right? And if we're being very dramatic here, if your heat transfer and work transfer both zero, aka when no heat is transferring into or out of the pipe and nothing is moving in the pipe, there's no vibration, there's no shaft rotating, there's no compressor, there's no pump, there's no turbine, no nothing. And because there's no heat transfer, the temperature of the pipe will not change. Therefore, your internal energy is zero. What happens is that only the kinetic energy, the potential energy, and if you guys remember, the flow energy changes. Have their sum of their changes will not change, right? It's constant, right? So the sum of the changes of kinetic energy, potential energy, and flow energy are going to be zero, right? In the realm of fluid mechanics, which is very related, right? Which is very related to uh, thermodynamics, this is what we call Bernoulli's principle, right? Kinetic energy, potential energy, and flow energy are conserved. That is another way of saying something like this, right? And as you can see, right, as you can see, let's highlight a couple of things here. Kinetic energy, this looks very familiar. Look at that, Vel squared over 2, right? Vel squared over 2. Well, for kinetic and for potential energy naman, let's just say potential energy, where is something that is related to the altitude of something? Z, Z1 and Z2. And finally, we have flow energy. What is flow energy here? Flow energy has something to do with the pressure now of the fluid. And so where do you see the pressure? You see it here and in here. So that is how we are supposed to look at Bernoulli's principle, right? Bernoulli's principle is a restatement of the first law of thermo, right? And that is how we're supposed to get to this conclusion. Okay? So yun lang naman. Let's move on. Next, we have nozzles, right? Nozzles are basically like, well, you can see what nozzles are, right? Or rather, you have an idea of what nozzles are in your mind, right? Ang problem na lang is that, well, what are they technically? They are defined as devices whose cross-sectional area decreases, right? In the flow or in the direction of flow, right? These guys are usually isentropic or adiabatic, right? And you've played with them since you were a kid, right? The quintessential, yun nga, yung hose example natin. You have a hose with water running through it, right? When you were a kid, you squeezed the end of the, you squeeze the end of the hose so that the water will travel faster out, right? Actually, my dad still does this for his gardening. So, there you go. Nozzles, right? Very intuitive, right? If you decrease the area, right? If you decrease the area of your flow, your velocity increases. At the very least, that is for fluids, right? Yeah, that is your nozzles, right? And you're thinking, or right, rather, you might be wondering, like, why it's isentropic. It's because, right, mangyayari, or more specifically, I think this is supposed to be adiabatic talaga, right? Adiabatic means that no heat flows into or out of the system. And in this case, the water, or rather the fluid, is traveling quite quickly such that the heat has no time to transfer into or out of the system, right? So kumbaga, the water, or rather the liquid, is traveling so fast that you're not going to remove or add heat in a useful manner. Right? So kung papainitin mo yung nozzle mo, hindi naman iinit yung mga tubig because, well, they're traveling so quickly, they're entering the system so quickly, they're also leaving it very quickly. So it won't have any effect on them. Kaya adiabatic or isentropic, right? On the other hand, diffusers are just reverse nozzles. By this I mean they are devices whose cross-sectional area increases. But still, they're ideally isentropic because still the fluid inside of these things, or the fluid traveling through these things, are very quick. So if you do decide to heat or cool them down, it will not have any useful effect on the fluid. Okay? And so for both of these things, right, they are ideally isentropic. And so as you can see, tanggal na yung ating heat. And plus, for nozzles and diffusers, how are you supposed to know if something has work or not? If something moves, right? If the nozzle or the diffuser vibrates, there's work. If something in the nozzle or something in the diffuser is turning or spinning, right? Like a blade, like a fan blade, there's work. But in here, usually there are no active moving parts, right? There is only the tube whose diameter changes. Okay, and actually, yun nga, nozzles and diffusers are also built usually horizontally. Why is that so important? Because if it's horizontal, is there a change in altitude? No, there's not. So you also remove your PE, right? And as a result, usually nga, ang lalabas na lang dito talaga sa mga devices na ito is, what do you call this? It's a balance between the kinetic energy of something and the enthalpy of something, right? These two things are conserved, okay? Next, we have turbines, right? Turbines are very important things or are very important devices for our current, uh, our modern life, right? These enable us to generate electricity from, I don't know, the combustion of non-renewable fuels or the combustion of, or no, the reaction, the fission of nuclear fuels or just the air around us, right? Ganon. And so turbines are devices that develop power from fluid motion, right? The combustion of the fuel is not the thing that matters. The combustion of fuel is there so that it serves as a heat source so that your fluid can move quickly, right? As you guys will learn down the line, right? We actually use steam, and that steam is the one responsible for moving very quickly. And yun yung nasasagap, that is what the turbine is supposed to catch, intercept, right? These fan blades are what's responsible for catching, kumbaga, right? Are responsible for catching, intercepting the energy, the kinetic energy, or what have you, the internal energy, the enthalpy of the fluid, fast moving fluid, so that it also can turn a generator, which then creates electricity for us. And just like before, right? Fluid here is running very quickly and it often has no time to like sit around and get heat. Therefore, it is again ideally again, this is ideally adiabatic, right? Or isentropic. Okay? So yun tayo for turbines. Boom, there you go, right? And in this case, right? In this case, what happens usually is that there's no heat, right? It's isentropic. And then, right? Turbines are also oriented usually, right? Horizontally. So there's no potential energy. And the thing here is that even though, right? Sabi ko earlier, right? Sabi ko earlier that some fast moving fluid will get slower because of the effect of the turbine catching, quote unquote, catching the energy, right? The change in kinetic energy is usually so small compared to the change in enthalpy. And so usually, I all that remains is the balance between work and enthalpy. What they mean to say here is that usually how much work or how much electricity you get from a turbine depends on how much the enthalpy changes. If the enthalpy changes a lot, right, edi syempre malaki ang iyong work. You have lots of work, you have lots of electricity if your enthalpy changes in a large manner. I don't know how to articulate that right now. Yeah, if your enthalpy changes a lot, you will get a lot of work, aka a lot of electricity. And so now let's go to the reverse turbine, right? Instead of getting electricity from fluid, right? Fluid movers are now responsible for giving energy to fluid, right? This is a pump, right? This is a pump. This is the an image of a pump, and basically fluid movers are things like pumps, fans, blowers, compressors, things that move air around, right? Things that move fluid around, right? Pumps are for liquid, right? Fans and blowers are for gases like, let's say, air, and compressors are a more general term, right? These are devices that impart fluid with energy. And again, just like before, when you're reversing something, well, you're not reversing the fact that it should be isentropic. Like with nozzles and diffusers, they are both isentropic even though they are quote unquote reverses, right? The inverse of a turbine, I believe, is a compressor, and both of them should be isentropic still because of the same way that we treat these things, right? AKA, fluid passes through these things very quickly, therefore they are isentropic. Okay? So again, we will see in here, same lang, right? Everything is the same in here except now, right? Except now, your work should be negative, right? AKA work in, yeah, because you are giving this thing work. Oops. You are giving this thing work. Let me go back here, right? And how do I do this? You are giving this thing work. Oh, sorry. That is not how I draw work. You are giving this thing work. Yeah. So work negative. And here, right? A turbine, what it does is that it releases energy so that we can use the work that is supposed to be inside, right? The energy inside of a very fast moving fluid, right? So yeah, right? The only thing in here that changes is the sign. And now, we have a special case of work computation for a pump. Yun nga, sabi ko kanina, a pump handles liquids, right? And usually, well, pumps deal with water, right? And there's a big problem with water, especially liquid water, aka compressed liquid water, right? We had this problem earlier where ang ginagawa natin is, oh, we don't have values for compressed liquid. So, ang ginagawa lang natin is an approximation, right? And what is the value of the enthalpy of water, of liquid water, of compressed liquid water? We have absolutely no idea, right? Ang alam lang natin kung paano i-approximate ay ang specific volume ng tubig, ng water at a compressed liquid, right? Compressed liquid state, right? And so how are we going to create a value for the delta H in here, right? What's going to happen is that, well, we're going to have to recognize that if it's liquid water we're talking about, we can kind of leverage the fact that for this subject, we assume liquids to be incompressible. Okay? If your liquids are incompressible, they cannot be compressed, right? From the direct word itself, it is not compressible. And if it's not compressible, that means that its volume doesn't change, right? Hopefully that line of logic is consistent, right? For you guys, hopefully that is consistent, right? If it's incompressible, the volume does not change. Therefore, not only can you think of pumps as being adiabatic or isentropic, in here, right, when they're considering working with liquids, compressed liquids, pumps may also be considered isometric. And if you guys remember, right, what is the steady flow work for an isometric process? It's this thing, right? It is this thing, right? Work steady flow for a process is going to be negative V times P2 minus P1, right? In this case, because things are flowing, right? Because things are flowing, you include a V slash instead, right? And now that now you have a dot, an M dot in here, right? Because, well, M dot is what we need in these kinds of equations. And if you're wondering, okay, which V should I get, right? And usually it doesn't matter, right? Usually it doesn't matter. This is going to be your VF at your first temperature, but usually you will also see in problems that kind of the temperature of water as it's being pumped does not change, right? So it doesn't matter usually if you take V1 or V2 as long as the temperature stays the same. But, right? But just for uniformity, let's all just take the specific volume at state 1. State 1 na lang. Okay? Yeah. Right? And mind you, this does not mean that your work is this thing because this is merely just our change in enthalpy. I will divulge this or I will explain more in the video I will send you guys, but yeah, that's it, right? Heat exchangers. All right. We're now going towards the end of this of this part of this lecture, mini lecture. I'm yeah. Okay. Now heat exchangers are very self-explanatory from the name, right? They are devices which interface, or rather, how do we say this more informally? Introduce different fluids to each other to exchange heat. They may or may not contact each other directly, but the introduction of these fluids or their parang contact, indirect or direct, right, in a closed space is the thing that allows them to exchange heat, right? They are ideally adiabatic. So a lot of things in here, again, are going to be adiabatic slash isentropic. And so, wait lang, you're telling me, right? You might be thinking now, like, wait a second, they're supposed to exchange heat. How can you say that it's adiabatic, right? Because when it's adiabatic, your heat is zero. How does that work? Right? How does that work? That kind of doesn't make sense. Well, now what's going to happen is that this happens, right? For heat exchangers, a lot of things don't matter. Yun nga, sabi natin, it's adiabatic. So you might be wondering already, like, why is it adiabatic again? I will explain in due time. These heat exchangers usually don't have moving parts, therefore, no work. And usually, again, right, changes in kinetic and potential energy in here do not matter that much because, again, these guys originally, they were in watts, diba? And then uh, when we were looking at delta H now, they are in kilowatts. So these guys are negligible, right? And usually I will tell you guys if something is negligible or not, right? Okay. Now, what does this mean? Your H is 0, right? Your delta H is 0. What does that mean? What that basically means is that in a heat exchanger kasi, you have two different fluids which interface. And you're thinking, wait a second, you just showed me, by the way, this is a picture of a condenser, right? It's a picture of a condenser. This is the condenser of a split type, right? A split type air conditioner. So what happens is that you just have the, are we using, no, we're using centralized air conditioning in Andrew. So what happens is that we just get the cold stuff now. And we usually don't have the very noisy, right? We don't usually have the very noisy uh, kinds of air conditioners in Andrew building, right? Because usually the noisy stuff, the compressor and the condenser are away from us. And then here the condenser is the thing that removes heat. So now I'm expressly saying, right? I'm expressly saying that there's heat being removed, but also that it is adiabatic. So it sounds very counterintuitive, and I will offer a counter explanation, right? The explanation is that in a heat exchanger, this is not the system. The system consists of two different fluids, right? One fluid is the one that's probably more important to us, but the other fluid is the one receiving the heat. For example, we have here a condenser, right? This is a figure, a symbol for the condenser, and the thing is basically the condenser in here Sino ba yung mainit? Who is the one rejecting the heat? Well, condensers use refrigerants, right? Refrigerant 22, refrigerant 134A. There are way more in the market these days, right? But basically, flowing in here is the refrigerant, right? In this coil right here. And what happens is that, for example, if this really is a condenser, you have a really hot refrigerant here that you want the heat to dump out of, right? You want to dump the heat of the refrigerant out to someone else, to something else, right? And so, how are you going to do that? You're going to have to interface it. You're going to have to introduce it to some other fluid. In this case, in the case of this, of this picture, it's air. Cold air comes in, or rather, cold air is introduced to the condenser, and syempre, because it receives heat, the refrigerant gives the air heat, right? Gives the air heat. What happens is that it will leave, right? It will leave hot. And then the refrigerant, because it has now dumped all of its heat into the air, it will now become colder. Right? And so as a result, ayan, ang mangyayari, cold air comes in, hot air comes out. Hot refrigerant comes in, cold refrigerant comes out. And so basically, this is the inside of a heat exchanger. And so you're still if you guys are still wondering why it's adiabatic, I will now close the system here. Do you see any heat coming into or out of the heat exchanger? No, right? There's no heat going like this, going out of the heat exchanger. All of the heat exchanging is happening within the heat exchanger, right? That is the point here. And so now I want to go back here. Why is your delta H 0? Delta H, if you remember, is just code for H out minus H in is equal to 0. If we move that to the other side, you will get H in is equal to H out, aka the total amount of energy you put in will be the total amount of energy you get out, aka, right? This refrigerant, I will call this 1, I will call this 2, I will call this air coming in A and then coming out as B, right? What happens is that the total amount of energy coming in from state 1 and state A should be the total energy coming out at state 2 and state B. Basically, H1 plus HA is equal to H2 plus HB. That is what's happening, right? If it so happens that your state 1 is hotter than state 2, if it so happens that your what do you call this, your state B is hotter than your state A, it doesn't matter how much or what the interactions are, so long as rather H1 plus HA is equal to H2 plus HB. If you guys have encountered Kirchhoff's laws, this should remind you of Kirchhoff's current law. The amount of current coming in should be the amount of current going out, right? This looks like a node in here. This looks like a node, and these are the branches, right? Alam ko naman meron kayong circuits, right? I remember that happening. Okay? And then I still haven't replaced the picture here. Now I will show you throttling devices. If you guys have what do you call this? If you guys have old refrigerators at home, you probably have seen some old refrigerators before. Old refrigerator expansion valve. You will see these coils, right? You will see these coils, right? And these are the ones that are usually hot. And again, hopefully, ma-recognize nyo, oh, these are the condensers I was talking about, right? And the thing about the what do you call this? the scale of these things, right? Look at the tubes. They are going to be much more thick or much more, yeah, tama. They have bigger diameter than what this copper thing has. Especially look at this coil here. That's so small, right? That's so small. The diameter of that is really small. Look at this, right? Compared to the rest of the tubing for the condenser, right? And so what does that do? Right? What that does is that it basically creates restriction. What do you mean restriction? In this case, throttling devices are devices used to reduce pressure by introducing restriction. Right? Restriction in the sense of restriction, okay. Restriction in the sense of you currently have a tube here and then suddenly you make it very small. The thing here is that your m dot, the whole of the mass flowing into here, still needs to go into here. And so what happens is that the pressure is reduced because it's very small. The diameter here is very small. If that kind of logic doesn't necessarily click with you right now, that's okay. Right? You don't need the amount of logic here. That amount of logic here, unless like you guys are going to take up uh fluid mechanics, in which case, sorry, that's the way things work, right? You can explore that more with Bernoulli's principle, right? A reduction in diameter means a reduction in pressure. But basically, this is the way the throttling devices use to introduce restriction, right? Look, you're gonna have to travel in this very tiny space. Another version is just a valve in general, right? A valve, you shut things down. You shut the flow of fluid down completely, or you just allow a really, really tiny amount. But still, the restriction is there, right? There's also this thing, I haven't seen this a lot, which is called a porous plug. There, right? It looks like a stent for the people here who are, I know, doing biomedical engineering. This is what they used out to like uh unblock the blockages in someone's heart, right? So porous plug, I really have no clue what these are. I won't give these the man. But suffice to say, these are what we call throttling devices. And they are ideally isenthalpic. Why? Because of the same things that were introduced earlier for heat exchangers, right? Usually there's no heat that goes into or out of this thing because, well, fluid travels here very quickly, right? There are no moving parts in throttling devices. I mean, like the valves you can open and close, but usually they don't open and close while in operation, right? No work. And the thing about here is that, again, these guys have values, yes, but usually they are insignificant compared to your enthalpy. So basically, what happens here is that your incoming enthalpy and your outgoing enthalpy are the same. It's just that the pressure of your state 1 is going to be much bigger than your state 2, right? Because they are used to reduce pressure. Okay? And then finally, mixing chambers and separators. This is actually what we were talking about in topic 4, right? Conservation of mass, right? If you guys remember that thing, that feed water heater, this is the actual version. This is the actual picture of a feed water heater, right? If you remember, right? You have water coming in and you have water going out. You want to heat this water. So what do? You introduce steam, very hot water, into the equation. So what happens is that steam mixes with cold water so that you can get hotter water, right? Feed water in, there you go, and then feed water out, right? Out, in. And then your steam goes into here. So kumbaga, it's kind of like this now. This is the shower head. I still don't know why it's introduced like this, but yes, there you go. Right? That's your mixing chamber. And in this case, right, if you guys remember, right, for a mixing chamber to work, the pressure should be ideally the same, constant. And there you go again, right? there's no heat that should leak out of the mixing chamber, and the mixing chamber usually has no moving parts, so there's no work, right? There's no Ke and Pe as well because they're insignificant. So again, your enthalpy should be the same. Your incoming enthalpy should be the same as your outgoing enthalpy. In this case, let's go back here again, right? What happens is that you will have, let's say, for example, here, state 1, state 2, and then state 3. The conservation of mass tells us that, okay, your state 1 plus your state 2, the mass flow rates of each should be equal to your state 3. Actually, there is a condensate drain line here, but let's not worry about that right now, right? This is what conservation of mass tells us, right? And then, what about the conservation of energy? Right? What about the conservation of energy? It tells us that the incoming enthalpy should equate to the outgoing enthalpy, aka H1 plus H2 is equal to H3. That is also valid, right? So you usually, in mixing chamber problems or separator problems, which are just basically reverse mixing chambers, right? You usually use these two in tandem. And you will see in one of our problems that we'll be solving soon, right? Is that mahaba-haba to. This is going to be a tedious process because you're going to look at a lot of things, right? 1, 2, 3, 4, 5, 6, right? That's it. And then, there you go. So, ayun, I will now pass this on to my past self, which is less sick than I am. We will do problems on steady flow devices. Okay? So thank you guys for listening. I'm really sorry again that I'm sick. I really thought I would make it for today's classes. Ayun. You guys take care. Please don't get sick. It's really hard.